like user interfaces and processing and started looking at some graphic stuff. We're going to be continuing on graphics at the moment, mainly because obviously one, it's quite important, and two, it's the theory that we're going to be teaching, particularly in today's lecture, is universal across any programming language, any graphics sort of graphics library or anything like that. Some of the calls may be different, but certainly the theory is the same. Oh, no. Now it's decided to read. Okay. So, yeah, same thing as everything before. So jumping straight in, because we've only got a short lecture today, graphics. So we're going to start looking at transformations. So we looked at this briefly yesterday, and in fact some of these examples, since this laptop is so slow, let's open processing in the background. Processing, there it is. Give that a chance to boot up. So we looked at the idea of transformations yesterday. So these are moving objects, rotating objects, basically any, well, transformation applied to an object. So obviously there's rotation, so you can rotate around the three axes of an object. So let's use this object here. So if we look at this, every object will have three axes because we live in a three-dimensional world. One will pass through, say, that way. Let's say that's our x-axis. Our y-axis will go this way, and our z-axis will go into the object. So rotation around the x-axis will rotate it that way, because we're basically, if you imagine you're sticking a skewer through it or something, and you're just turning on that, so an x-axis will rotate that way, y will rotate that way, and z will rotate that way. So the three axes will always, all the stuff we're going to be dealing with, the three axes will always be orthogonal, so they're always at 90 degrees to each other. So yeah, in processing we can rotate around the various axes by saying rotate x, rotate y, rotate z, and then passing in the amount we want to rotate by. So depending on, we looked at this a little bit last week, depending on whereabouts the state of the coordinate system, when we call rotate, we may rotate, we're going to rotate around the origin of the coordinate system, not necessarily, or let me think about this. We're going to rotate around the axes of the coordinate system, not the axes of the object necessarily. So, you know, we might say the x-axis of the object goes through this way, but if the x-axis of our coordinate system goes this way and we say rotate around x, we're actually going to rotate that way, not that way as we might expect. So rotations in 3D geometry are probably one of the hardest things to get your head around, unfortunately, because you have to keep in mind that, you know, as you move things, as you rotate things, it's going to affect it, and you know, the order of operations you do will affect things as well. So we looked at this a little bit last week with the arm example. This one down here, you know, if you do a transform and then a rotate, you get a different result than if you do a rotate and a transform, or translate, sorry. So yeah, anyway, we'll look at that in more detail later. So yeah, rotation, rotate around x, y, and z. And translation, we can translate around, well, in processing there's a translate for x and y, so that just won't translate in the z dimension, or a translate x, y, z. Obviously, if you just wanted to translate in x or y, you just set the other value as 0. So if you just want to translate in z, you just say translate 0, 0, and then whatever amount you wanted to translate in z. And then there's scale as well, which we didn't look at so much, but it's pretty straightforward. You just say scale x, scale y, scale z, and it will scale in those dimensions. So a scale is just basically resizing. So if we had this object and we said, and let's say the x-axis goes this way, we said scale x 0.5, it would be half as long as it was before. We'll look at some more examples of scaling later. And we talked about the idea of push and pop as well. So saving the state of the coordinate system, so saving the orientation of the axes, its position, its scale, and then with push and then pop we'll retrieve it, and it's a stack. So we save the state, we save the state, we save the state, we save the state, and then we can pop back through to any prior time. And I'll give you guys probably a little assignment to do, which will, you know, give you all a bit of experience playing with push and pop and rotate and translate. All right, so let's have a look at some of the math and everything behind it. So you guys, you know, don't be worried if the math is over your head, because we're not testing you on, this isn't a 3D graphics course. This is just, you know, for those of you who are interested in how it works, Turn the light off. So if you're interested in how it works, we've got the math there for you, but really all you need to know is what the function is and how it's going to affect what's happening in the 3D scene. So we have the function translate tx, ty, tz, or alternately we can just do translate tx, ty if you want. But basically all that's going to do is it's going to physically shift our 3D model. So it's going to take it and it's going to move it somewhere else. Oh, that's a really annoying noise. This is basically what's actually happening in the math. So every x, y, and z position. So you remember when we looked at models like what they're composed of last week, we said, okay, you have a bunch of vertices and you can use those to define quads or triangles or whatever else. But each point on that quad or each point on that triangle is represented by a vertex. And this is essentially what's happening when we translate. So we have our original x position. So we say, okay, there's a vertex at 0, 0, 0. And then we say translate by 5, 5, 5. Basically what we do is we go, okay, the new value of x is the old value plus the transform. So it's 0 plus 5, so this will now be 5. This is 0 plus 5, this will now be 5. This is 0 plus 5, this will now be 5. And so our translate by tx, ty, tz will basically take our original thing and just add the values to that. Now there's another common thing you're likely to see when you play in 3D geometry, particularly the longer you go, and it's transformations written in this form. So this is a 4x4 matrix which basically represents the state of our coordinate system, our coordinate system, our entire scene. So we have basically this 3x3 block in here will represent rotations and scales and all these sorts of things. And these ones down here will represent transformations or translations, sorry. And across the bottom here, this is basically it's a homogeneous coordinate system, and this basically represents that everything is a point. So you need this in here so that when you multiply everything out, it comes out as a point. If this isn't 0, 0, 0, 1, you're going to end up with some funky geometry where lines which used to be perpendicular or parallel will no longer be there. So when you see these things, this bottom line should pretty much always be 0, 0, 0, 1. And sometimes you'll actually see that bottom line just removed, but just know that that's what the bottom line looks like. And then this is our original point. So if we're defining, okay, we have we're defining a triangle and one vertex on one of these, or one of the vertices of this triangle is at x, y, z, and we denote this as a 1 because that defines in the math that it's a point. If it was a 0, it would be a vector, so a line which passes through a point but has no defined start or end. So we've got a 1, it's a point, and its position is at x, y, z. And then if you guys have done much sort of this style of math, you can actually multiply this out by, multiply this by this matrix, or this vector by this matrix, and you end up with this x prime, y prime, z prime, 1. Again, it's a 1, it's still a point, but this is the new position. And if you actually go to the trouble, I'm not going to do it because I always need to look up how to multiply matrices, because no matter how many times I do it, I can never remember how it works. But if you actually took this and multiplied it out here, you'd see it basically be, for the x column, 1 times x plus tx, 1 times y plus ty, 1 times z plus tz, which is 1 times x plus tx, 1 times y plus ty, 1 times z plus tz. So this, if you write it out in full form, will give you that, which is where we started at anyway. So, with the translation example, it's pretty trivial. So let's move to scaling now. So scaling, as I said before, we're basically like resizing the origin. So if we scale by half, it basically, in one axis, it basically means everything in that axis will be half what it used to be. So the function for it, sorry, I think I had this wrong before. I think I said scale x, scale y, scale z. It's actually just scale, and then you define sx, sy, sz. So if we wanted to say scale half size in sz, what we'd do is we'd say scale 1, 1, 0.5. So we basically define 1 basically means leave it as it is. 0.5 will halve it. Anything greater than 1 will increase the size. 0 will decimate it, so it basically flattens it to an infinitely small point. Less than 0 will flip it, basically mirror image. So, you know, if you imagine you draw a line out this way and then you scale it, it gets smaller and smaller, and then once you go into the negatives, it'll actually scale backwards. So if you have a 3D model and you want to flip it, like a mirror image, you can actually scale it by negative, well, if you do -1, -1, -1, it will scale it. So if this model goes out this way, it'll go out that way. Or you can just flip it if you did say you want to just mirror it in the z-axis. If you just set sx to -1, it'll basically flip it that way. Anyway, not going to spend too much time on the math again, but this is basically what it looks like. S times S of x, y times S of y, z times S of z will basically multiply these out, and that makes sense. Like, you know, if we say that, you know, 0.5 will halve it, or halve the value of z, z times 0.5 is just going to be, say if this is 10, 10 times 0.5 is going to be 5, sort of thing. And as I said, if we do 1, it'll remain the same. X times 1 is just going to be x, so on and so forth. If it's 0, it'll decimate it, so anything times 0 will come out 0. And this is what the matrix form of this looks like. And again, if we multiply this out, it'll be that times that plus 0, that times that plus 0, that times that plus 0, which is what we've got here. So scaling is always about the origin. All of this stuff is about the origin of the coordinate system. It's not around the origin of the model. So if we have, let's say the origin is here, and then we have at distance 5, we start our model, and then we halve it, what's actually going to happen is the model is going to move over by half and then scale down by half as well. So it's not like the model is just going to get smaller. It may appear to shift as well because we've actually grabbed the whole world and shrunk it down. So a distance of 5 in the translation will now actually only be distance of 2.5. Does that make sense to everyone? Hopefully, yeah. So yeah, there are different types of scaling. If it's greater than 1, it's a stretch. So we're basically grabbing it and we're stretching it out, making it bigger. If it's 1, it's no change. If it's greater than 1, or greater than 0 but less than 1, it's a shrink, so it's going to squish it down. If it's 0, it's decimate it. So if you try and scale a model at 0, it will just disappear from the scene. You know, because we can't render infinitely skinny things, so we just don't render them. -0, greater than or less than 0, greater than -1 will reflect and shrink, so it's going to flip it, but it's going to be smaller. -1 is reflect, and greater than -1, or less than -1, I guess, is reflect and stretch. So this is basically, you know, this is a separate slide, but technically it's the same thing. Who keeps trying to call? Go away. So yeah, this is, you know, scaling with a value of -1. So -1 in the x dimension. So this is the x-axis. So this is the x-axis here, and if we say scale -1, 0, -1, we're basically taking every value here and inverting this. So if you imagine this, everything on this point in this line is 1. When we multiply it, it's going to be -1. Everything here is 2, so that's going to be -2, so on and so forth. So you can basically see how these points map to here, here, and so on and so forth. And this is a reflection across y, so this would be -1 in here. And yeah, if you want to basically reflect in the YZ axis, it's a scale in -1 in the x, the MZ axis, so on and so forth. But yeah, it's just different ways of looking at the same thing. Right, before we get into rotations, anyone got any questions about that? Because it's about to get worse, unfortunately. Let me just.
The MZ axis should be a negative y value, right? The previous the m of xz should be a negative y value.
M of xz.
The first one.
M of yz would be a flip in zx.
Yeah, m of xz. The
second one.
Yeah.
Is a negative. Yeah. It's all right. I wouldn't be surprised if there are the occasional mistake in the slides. I'd like to think I've gotten rid of most of them throughout teaching this course, but perhaps not. All right, so rotation about the z-axis. So rotations are where it starts getting kind of complicated. Well, the math starts getting a lot more complicated anyway, but theoretically it's the same. You just got to try and think about if I was trying to manipulate this object in the real world, what would happen to it. So rotation about the z-axis, so if this is our coordinate system, we have our x-axis goes that way, our y-axis goes up, and our z-axis, it's unfortunately very hard to show 3D geometry on a 2D screen, but the z-axis is essentially sticking out of the screen towards you guys. And if we're rotating around the z-axis, it basically means we're rotating that way. And every object every object in the scene will rotate around that x-axis. So if you imagine this is attached to my arm with a stick sort of thing, so that it rotates at the same speed. So you can see here I've got this triangle, and as we rotate it around the x-axis, it's going to move like that. Rotate z is the command. And this is basically what the math looks like. So x cosine theta minus y sine theta, and x sine theta plus y cosine theta. I'll leave you guys to figure out why that works, but it does. And z prime and a rotation around the z-axis, the z values will always be the same. So if you think about it, the z values are where its position as it sits out here. So let's say this is sitting at 1 on the z-axis. As it rotates around, that's still going to be at 1, but its position in the x, so this one here used to be here, now it's over here. This one here used to be here, now it's here. And the y value, so used to be here, now it's up here, here, and here. So those change, but the z value stays the same. Rotation around x-axis, same thing. So x is now this way, so it's here, and we're going to rotate objects around that way. Rotate x is the command, and the formula, if you look, is very similar. Cosine theta minus sine theta plus cosine theta, and all the x values remain the same. So all their values along here are the same. It doesn't look so much in this diagram, but that and that and that one actually as well, would all be the same x values. It's just because I tried to fold it out orthogonally on their screen. It looks weird. But all those values will actually have the same x value. And finally, rotation around the y-axis is the same thing. So now we're rotating around that way. Rotate y. Same formula again. Cos minus sine, sine plus cos. And what's changing effectively is the order of these, so x, the y, the z. Again, you guys don't need to know this, or don't need to understand how it works. It's just there if you want to look into it. All you need to know is the commands, x, y, z, and what they're going to do to the scene. So you need to be able to say, okay, this is the current state of the scene, and if I call rotate x, this is what's going to happen. If you guys want to learn the math behind it, you're more than welcome, but it's kind of out of the scope. All right, so we talked about this again briefly last week and looked at some examples, but the order of transformations does make a difference. So if we have these two, just ignoring everything on this side for a second, we have these two arrows basically, which are drawn on the scene. And one of them, we're going to do the same two commands, a rotation followed by a translation, but we're going to do them in different orders. So in the first one, we rotate the arrow, like that, and then in the second one, we translate it out. So we do a rotation first, and we always rotate around the origin of the coordinate system, if you remember. So this is the rotation, or this is the origin of the coordinate system, so the rotation is going to be around there, so we do that rotation, that's where we are now. And then we do the translation, which will shift it along that way. So if we do the same thing, but with the same two commands, but in the opposite order, we do our translation first. So we do that shift. So this is exactly the same values, exactly the same amount. We're going to shift the arrow out here. But now when we do our rotation, because we're rotating around the origin of the coordinate system, that's actually going to rotate all the way around there. So you can see by doing the same two commands, but in a separate order, we end up with different results. So this one, the arrow has been rotated around the base of it and positioned. Here, the arrow is actually being rotated around here. And if we had an incremental counter which did this arrow would spin on its point, whereas this one would orbit the origin of the coordinate system. Make sense? Hopefully, to some extent. So yeah, composite transformations. It's very common that you'll be wanting to do more than one thing. There's not too many 3D scenes where you just say, okay, well, let's just move that one there and that's all we're going to do with it. You might want to do a rotate, you might want to do a scale, you might want to do a translation. And this is basically, in the math, this is how it works. So Q1, Q2, Q3 are those 4x4 matrices we saw before. We've just basically slammed them down and said that Q contains everything. But if we start off with our XYZ point, so this is our vertex in a triangle or a quad or whatever else, we multiply it by our first one, we multiply it by, and then we get the results out of that, we multiply that by the second one, we get the results out of that, we multiply that by the third one, we get the results out of that, and then we have our final thing. So the order of transformations will, in this case, it does Q1 followed by Q2 followed by Q3. Again, I've yet to find a way to explain this better. The best thing I can sort of say is grab one of the examples and try swapping, find a nice simple one like that ARM one we looked at, try swapping the order of operations, see what happens when you put the rotation and translation first, try and guess what it does before you run the code and see if you can do it. Okay, so one thing which we fairly commonly want to do, which is harder than you'd think it would be to do, is to rotate an object around a pivot point. So, we sort of said early on, let's say that this thing has its own sort of coordinate system. We define X is here, Y is here, Z in here. But, the coordinate system of our scene is always going to be, is going to be somewhere else usually. So if the origin is here and this object's here and I do a rotate, it's actually going to rotate all the way around there. But what if I just want this thing to rotate on its own axis? So, everything else in the scene stays where it is, and this thing just sort of rotates around here rather than orbiting it like a moon orbits a planet. Basically, how we do that is we move the origin of the scene to be where we want the rotation to happen. We do the rotation, and then we move everything back. So it's effectively like, okay, if our origin is down there, and we want to rotate this object around here rather than rotate around there, what we do is we actually bring this down to the origin, rotate it, and then move it back where we started from. Or vice versa, we move the origin of the scene up there, but it's a little bit difficult for me to lift the whole room, so you just have to imagine what I did, but shifting the whole room rather than vice versa. So this is how it looks. So depending on what way around you're doing, it'll either be negative, negative. So this is basically the position you want to rotate around. So if, say, this is sitting at 10 by 10 by 10 in the coordinate system, and I want to like this point here is sitting at 10 by 10 by 10, and that's where I want to rotate around, I'll translate by negative 10 by negative 10 by negative 10, and that will effectively move that back to where the coordinate system is. Then we do the rotation, and then we push it back out to where we started from. So otherwise, I think these should probably be the other way around, sorry. I thought I'd fix that last time around, but apparently not. But yeah, the idea is you basically just want to figure out where you want to rotate the scene around, move to that point, rotate, and move it back again. So in this example here, we're going to move, so if this point is at xp, yp, zp, we're going to translate by negative xp, negative yp, negative zp, and that will pull this triangle back down, so that point is sitting at the origin. Then we're going to do our rotate, and then we're going to push it back out where it came from, and that will effectively rotate our triangle around that point. Yeah, so we addressed this a little bit yesterday. So we sort of covered more yesterday, on last Thursday. We sort of covered more on Thursday than the lecture slides did, but that's okay. But we're sort of looking at, okay, we've looked at how you start translating and rotating things and it affects the entire world matrix. What if you have more than one object? What if I've got an object over here and an object over here, and I want to rotate this one around its point, but I don't want to rotate this one? If I shift them both down and do a rotate, they're both going to rotate. When I pull up, this one's now going to be over, rotated that way. So how do I get around that? These transformations accumulate. It's going to become an absolute nightmare as soon as I have more than one object. Say, want to rotate one, but if I rotate something, it's going to rotate everything in the whole world. So yeah, different sets of transformations to different objects. Transformations accumulate. So every transformation I do is going to affect everything. And if it takes 3 commands just to rotate an object around a point, if I want to keep one object still while I rotate another one, that's going to take at least 6, because I'm going to have to rotate one object and then rotate the other one back to where should be. So the solution, well, basically the main solution that we're going to use is, is this one down here, but we'll look at the other one. So one thing we can do is reset the matrix to identity. So the identity matrix is, I don't think we actually have it in here, but if that was not a -1, if that was a +1, this is known as the identity matrix. So this is basically all zeros and ones in the diagonal, and that states the x-axis runs along the x-axis, the y-axis runs along the y, z runs along the z, and everything starts at 0. And this is when we first start, we call size 512, 512 P3D. Processing will tell OpenGL, okay, set up my 3D environment, and OpenGL will basically say, okay, this is the current state of the world. Y is pointing in Y, X is pointing in X, Z is pointing in Z, and everything starts at the origin. So what we could do to get around this problem is we could just reset the matrix to identity. So we could basically say, okay, we've positioned that object, it's sitting where I want it to be. Now let's set everything to 1, 1, 1, 1, and all other zeros, and then we'll just start again from the beginning. This is perfectly happy to do that, perfectly relevant. Sometimes it is the best option. If you're drawing a scene and, this object is completely separate to that object and you don't really want any sort of correlation between them, it may just be easier to say, okay, load the identity, and in fact, we'll have a look. I'm guessing, I know OpenGL has a load identity function, I'm sure processing does as well. Yeah. Okay, so not an obvious one, but I'm sure there's one in there. So there will be some way to reset the matrix to identity. Undo a transformation by multiplying its inverse. So, if we translate out 10 units in this direction, we can basically get the transformation matrix back by doing 10 units in this direction. Or if we rotate 30 degrees around this way, we can rotate 30 degrees back again to get back to where we were. So we can always undo a transformation by multiplying its inverse. So if we know what the transformation was, we just do the opposite of it. We do, instead of rotating by 30, we rotate by -30. Instead of moving by this, we move by that. Instead of scaling by 2, we scale by half. So on and so forth will get us back. But that requires us to remember every transformation we've ever done in order to undo them. Easiest way to do it is use a stack. So this is what we looked at with push and pop. We discussed this quite a lot on Thursday. Basically, you save the current state of the stack, save the current state of the coordinate system, and then you can retrieve it. And this is what I tried to draw on the board. Hopefully this makes it a little bit clearer. So CT is our current transformation. So it starts off at nothing, and then we do a translate and a rotate, and we call push matrix. And so that will basically say the current transformation is So the current transformation is a translate and a rotate, and then we call push matrix, and that will save the state of the current transformation. So, this can't be touched. We can't modify this bottom one anymore. The current transformation is now this. So when we first call push, it's going to be exactly the same. We're basically just saying save a state. We're not changing it at all. We're just saving it. Then we do a scale. So now the current transformation is equal to a translate, a rotate, and a scale. And we still have this translate and rotate state saved. And then when we call pop matrix, we basically remove that top one off and set the current transformation back to that. So we've effectively undone the effect of the scale. So we could have done scale -SX, -SY, -SZ, and it would have done the same thing. Well, actually not negative, sorry, that it would be like 1 over SX, 1 over SY, 1 over SZ would undo that scale. But it's often a lot easier just to say, okay, push matrix, do whatever manipulation we need to do here, and then pop matrix. So in this case, we're drawing a cube at this point, so it might be that we're drawing a lot of cubes. So we start with a big cube, and then we shrink down to a smaller cube, and shrink down to a smaller cube. So it might be easy, okay, let's position where all our cubes should be, and push the matrix, shift over, and do a smaller cube, and pop matrix, and then we can get back to our big cube. Or we could do a cumulative, so we could draw the big cube, push matrix, shift scale, do another cube, push matrix, shift scale, do another one, and then we go pop matrix, pop matrix, pop matrix, pop matrix. So at any point in time, we can get back to where we were before. So there are demos. Push pop demo. I don't know where this is. Push pop demo, push pop cubes. For some reason I didn't actually put. Let's see what this one is. Normally I write down the whole path to them in the executables thing, but let's have a look and see what this one gives us. So here is an example. These are a whole ton of cubes which are all drawn on top of each other. So you can see we push, we rotate, and then we pop. So we basically change the position or change the rotation of the world, draw a cube, pop back to where we were, change, like rotate it differently, draw a cube, and go back to where we were. So if we comment these out, let's have a look and see what ends up happening. So basically we're changing it from each cube gets rotated its own certain amount to each time it gets rotated relative to the cube before it. And you can see it's just chaos now. Like everything before, it was like first cube should rotate 5 degrees, second cube should rotate 10 degrees, third cube should rotate 5, 10, 15 degrees. Whereas now, basically what's happened is we've said first cube rotates 5, second cube rotates 10 plus 5 is 15, third cube rotates 15 plus 10 plus 5 is 30. So all these rotations are accumulating. And in the first one, it's actually quite beautiful in its own way, but in the original one, you can see everything sort of stays locked and stationary to where it is. So each cube, if you sort of follow it round, will stay locked in its relative position, whereas in the new one, everything's going to rotate, they accumulate, so they speed up and they get faster and faster and faster and faster, or they're rotating greater and greater amounts, and then it sort of looks like they slow down and then they start reversing in the opposite direction because there's only 360 degrees, and if you rotate over 360 degrees, you're effectively rotating backwards again. Yeah, so everyone get that? Make sense? Yep. So this is a little example which sort of explains a little bit more why or when this would come in useful. So let's say we're drawing a little 3D world. We're popping down some houses and stuff. It's going to be all cute. So we draw a house, and this is often how your scene might be built. This is sort of quite a logical way to do it. So we say, okay, we have a house object. So let's push our matrix, translate to where we want the house to draw, scale to the scale we want the thing, and then we're going to call our function which draws the house, and then we're going to pop matrix. So this push matrix and this pop matrix, we're basically saying this is the beginning and the end of drawing an object. We don't want every other thing in the scene to be relative to this house. We just want this house to be here, and everything else will just go wherever we put it. So down here we have a tree, for example, so we push matrix, push it out, and then pop matrix. It would probably make more sense if these were actually different to these ones, but that's neither here nor there. But, we probably don't want the tree relative to the position of the house. A house should be where a house is, a tree should be where a tree is. A tree shouldn't be where a house is plus some offset, unless you choose to do it that way, which is, depending on which way you do it, probably doesn't make a lot of sense. But anyway, so we push it, we move everything, move the whole coordinate system to where we want our house to be drawn and scale it, and then we call our house function. And our house function, now every part of the house is defined relative to the start of the house. So, if we have our house here, our door is going to be here relative to the house, our window is going to be here relative to the house. That makes sense because your door is part of your house. You're not going to say, okay, draw a house here, reset the coordinate system, and then figure out where the door should go. The door is part of the house, so it should be within this push and pop. So you can see here, we're basically going to say, okay, start drawing a house, and then we're going to jump in here, we're going to say, okay, the door should be at this position on the house. So the door should be 2 by 0 by 0. So we're going to shift in, probably make more sense if it wasn't 2 by 0. So let's say the origin of the house is up here, we're going to move down to here, we're going to draw our door. So every time we call this house function, the door is always going to be in the same place because that's where a door goes on a house in this world. So we push it, move it, and then pop it, and then we say, okay, let's do a window now. So we're going to push matrix, and we're going to translate over here, and then we're going to call our draw window function, and then we're going to pop back. So by doing this, every time we call house, we're guaranteed that the door is always going to be in the same place in the house, and the window is always going to be the same place on the house, regardless of where the house is. So you can imagine now if we wanted to build a city or a little town of these houses, we could just say push matrix, translate, scale, house, pop matrix. Push matrix, translate a different amount, scale a different amount, draw a house. Push matrix, translate another amount, scale, and basically what we're going to do is we're going to go, boom, draw a house there, and the window and the doors and everything will be relative to that house. Then we're going to pop, and then we're going to push, and we'll say draw another house here. The windows and doors will be in the right place, pop back. I'm going to come over here, the windows and doors will be relative to that house, and so on and so forth. Right, I think we've got, yep. So we'll get through these last two slides, and then we will call it. So you can see this sort of starts getting quite complicated quite quickly. We've got to try and, in our mind, sort of say, okay, well, here's an object, and here are all the subcomponents of that object which are related to it. So, this is the same idea as we were looking at a while ago with classes. So a class encapsulates an object and all the properties in it. So we had our car, for example, and our car has a speed and, position and all these things. And basically what we've done here is we've sort of taken that encapsulation to the next level. So we're not just saying a car has a speed and a position. We're saying, okay, well, a car has a speed and a position. When we're drawing it, though, we have the car has wheels, and the wheels should be relative to this position on the car. So we're basically not just describing here's an object and here are its properties. We're saying here, when we're drawing an object, here is where all the subcomponents of that object should be drawn relative to it. So, the wheels on a car should always be in the same place relative to a car. There's always going to be one set so far back from the front of the car and another one set so far forward from so far back from the front and so far forward from the back. Like the wheels on a car are always in the same place. The wheels don't move independently of the car, ignoring suspension and stuff like that. But, the wheels are always going to stay attached to the car, otherwise you've got a problem, which did happen to me once. That's a story for another time. The wheel. It wasn't actually my car, it was my friend's, but the wheel came off while we were driving. That was fun. Okay, anyway, so you can sort of see if we're doing all this stuff like this, this is a perfectly valid way of doing it, and this is how people have been doing it since 3D graphics has been around, and people still do it these days. However, there is actually a better way to do it, which sort of encapsulates a lot of this functionality. I'm just going to mention it because you might be sitting here going, how the hell do people do these enormous big scenes which have got thousands of objects in it and all these other things? And what they actually use, often use, this isn't the only way of doing it obviously, but one of the common things is what's known as a scene graph. So scene because we have a 3D scene, and a graph because, well, you'll see in a minute. But basically a scene graph allows us to represent the entire environment in a tree structure. So maybe it should be called a scene tree, but that's neither here nor there. I guess you can have things, you can sort of break the tree thing. So if you guys don't know what a tree structure is, in computer science, basically a tree, you have a node and then it has one or more child nodes, and each of those have one or more child nodes. And you might be asking, well, how is that a tree? Well, if you turn it upside down, it looks like that, and then we go, whoa, look at that, it's a tree. Amazing. I'm not an artist, in case you couldn't tell. But yeah, so, that's a tree. A graph actually allows you to do weird things as well, so we can actually connect nodes all over the show. So a tree, each node has only children node. A graph allows you to do other weird things, which you can do in a scene graph, but to be honest, if you're doing a scene graph and it's starting to look like that, you've done something wrong. Unless, I can't think of an example when that would be correct. But anyway, so a scene graph allows you to basically define, okay, here's an object, here are all the sub-objects, and so on and so forth, and basically does exactly what we did in code here, but it does it in a data structure. And there are a bunch of other benefits, so using various things. So obviously, rendering all these things comes at a cost. So for every polygon you draw on the screen, so every triangle, every quad, there's a processing time. The more you draw, the slower it's going to be. If you're drawing things which you can't see, so if you have an object here and an object here which isn't visible, and you draw both of them, obviously there was no point drawing this object because it's invisible anyway. If you have your view window here, so this is what you see, and there's an object out here, or there's an object behind the camera, you draw that, you've wasted processor cycles. We're not going to get into that because that's, again, a whole topic unto itself, which we just don't have time to cover. But scene graphs basically can do some cool little functions. They can sort of say, okay, what is outside of the viewing window? And normally you might do this test, if you're writing this yourself, you might do this test. Let's go back to this example and say we're back to a tree. You might say, okay, is this one inside the window? Is this one inside the window? Is this inside? Is this inside? Or like, can it be seen? Whereas a scene graph just says, okay, is this one in the window? No, it's not. Okay, let's just not draw any of that. And you can imagine if you've got millions and millions of things underneath that, you've basically saved yourself a huge amount of processing time just by doing one check rather than having to check each individual object. This is what a scene graph looks like. So you have what's known as the root of the scene, or the root of the tree. And then you do things like, okay, let's draw our house example that we saw before. So we're going to transform our scene, which is exactly what we saw before. We translated it, we scaled it. Then we're going to call our house. Now our house has a transform and a window. And then we have a transform and we draw a door. And on the door we transform and have a door handle. So all of these things, you can look at this. And this is quite a lot easier to sort of visualize and process than the example we saw with the code. Like in the code, you can sort of look at it and say, oh, here's a house function. Hopefully everything within the house is within this house function. This sort of explicitly defines it. So we can look at this and say, okay, well, all of these objects underneath the house are all going to be drawn relative to the house. So any transform I do here is going to affect all of these. So if I move this if I start the origin and move by here, we know all of these are also going to be moved by here, and so on and so forth. And internally, this actually breaks down to the code we saw before. So what we'll do is every time we visit a child, we basically say push matrix, and then do that, and push matrix, and do that, and push matrix, and push matrix. And then when we start going back up, we just go pop matrix, we end up back here, and we do this, and we go push, 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 pop, 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 and then we're back at our scene root, and then we just go off and do our next thing. And I think that's all we have time for today, yes? So you guys need to rush off to your health and safety induction. If you were one of the 2 people who went yesterday, you don't have to go. But yeah, otherwise you do, because unfortunately it is university regulation, but you just have to get it over and done with. And let me just have a look. It is in E421 in the Civil Mech building. So does everyone know where that is or can find it? Oh, okay. Well, yeah, maybe these 2 can walk you over there. Otherwise, but yeah, it's one of these things you have to do. Otherwise, Mark will be taking you on Thursday, and I might see if I can whip up a simple little assignment for you guys using processing and graphics and getting a chance to do some translates and some rotates and some push matrices and pop matrices and everything else. Hopefully it'll be a bit of fun. All right, cool. Yeah, otherwise, if you've got any questions, you're always welcome to email or pop by my desk and we can have a chat about it.